Hey everyone. Today is lesson 3 on first principles. Now what we've done already is we've discovered limits, and we've looked at getting the limit coming from the left and getting the limit coming from the right, and then also just in general what a limit is and how to calculate the limit. If the limit is the same from the left and from the right, we can just call it one limit. We don't have to call it the left side limit and the right side limit. I want to take you back to the very first day where I gave you that kind of introductory investigation. And one of the things that we were looking at is we were discussing how to estimate the slope of a tangent line at any given point on a graph. Okay, what first principles is going to do is it's now going to allow us to calculate the slope of any tangent line on a graph. Okay, so here's what we're going to do. I would like you to draw the graph of y equals x minus 2 squared minus 4. We're going to start with something you know. You know this is a vertex that opens up. It has, this is a quadratic that opens up. It has a vertex at 2, -4. Okay, and then I want you to label that vertex and draw a tangent line that would pass through the vertex. Okay, very similar to what we did way back on day 1. Something like this. And then the vertex, the tangent line that would pass through the vertex would have a slope of 0. Okay? Okay, now we're going to draw a secant line. Now we're going to plot the point 4, 0. Okay, so you can see that right here. And we're going to draw a secant line that passes through this point and the vertex. Okay, so that will look something like this. So a secant line hits the graph twice, a tangent line hits the graph once. And we would try and determine the slope of that line. Well, that's fairly easy. From this point to this point, we're going to go up 4/2, so the slope would be 2. Okay, nothing strenuous yet. Okay, now we're going to move this point a little closer to the vertex, and then a little closer, and then a little closer, and then a little closer. What is happening to the slope of the secant lines as we move our point closer to the vertex? What I want you to say is the slope of the secant line will approach the slope of the tangent line. Now, think about the last 2 days that we've had. As soon as I say the word approach, your brain is starting to churn and you're thinking, when I approach something, that's calculating the limit of something, right? Interesting. Okay. So at this point, as the point approaches the vertex, the slope of the secant line approaches the slope of the tangent line. All right, if we moved our point to the other side of the vertex and repeated the same steps, would anything different happen? So let's say I was here instead, and I drew my secant line like that instead. Okay, and I started moving that closer and closer to the vertex. Would anything different happen? No, actually nothing different would happen except that all the slopes would be negative. But those negative slopes would still approach the slope of the tangent line of the vertex. Okay. So nope, the slope would be negative instead of positive, but it would still approach the tangent slope as our point moved closer to the vertex. All right, so I'm just going to show you this on GeoGebra for a sec. So I'm just going to switch over to GeoGebra. Okay, so this is a dynamic representation of what we just did. Okay, I've got the parabola here. It's got the vertex at 2, -4. I've drawn in my secant line, and right now I have my secant line going from the vertex to that point 4, 0, just like you graphed it. Okay, now what I'm going to do is I'm going to take that secant line and start approaching the other line. And as I do that, I want you to look over here. You can see that my slope is now 1.84, and then I just keep going, and it keeps getting smaller and smaller as it approaches. And you can see the slope also approaching, and so we get to the point of tangency. Okay, so if I was on the other side, same thing would happen, except that all my slopes are negative. So you can see there that it's -1.9, -1.7, 1.4. Okay, and as I approach that line, or as I approach that point of tangency, the slope of the secant approaches the slope of the tangent line, okay? Now, remember what we want to do here. We want to calculate the slope of the tangent line, right? So we are going to take a secant line and use that to help approach the slope of the tangent line so that we can determine what the slope of the tangent line is. Okay, so let's just switch back to the PowerPoint. Okay, so how are we going to do that? Well, actually, I'm going to show you two different methods to do that, okay? And you do want to be comfortable with both methods, but both of them just involve limits. So let's draw the same graph again. This time we're going to randomly choose 2 points. So I'm not going to place myself anywhere that I know, okay? So because our 2 points are random, I'm going to call one point A. Now, if I call one x value A, the y value has to be f of A, right? Because I'd be putting A into the function. And so the x value will be A, the y value will be f of A. I could have just as easily used B and f of B or C and f of C. Point being, A represents some random x value, and f of A would represent the output if I put that random input in. And my other point is going to be x comma f of x. So I'm just going to randomly label them in 2 different spots, okay? So I have x comma f of x and A comma f of A. Okay, what would happen to the slopes of the secant lines as we move x, x comma f of x closer to A comma f of A? Okay, so if I'm moving this point closer to this point, the slopes would end up approaching the slope of the line that's tangent to A. Okay, so if I had a secant line, let me draw that in for you for a sec. Just like we did on the other example when we were fixed to the vertex, here is the secant line. And what we're saying is, here's the tangent line that we ultimately want. Now, I'm just kind of throwing that in, so I may not do a good job of drawing it as a tangent line. Okay, but what we're saying is, as we can make x, the point x comma f of x, approach the point A comma f of A, that secant line is going to, the slope of that secant line will approach the slope of the tangent line that we actually want. So what we can do is we can figure out the slope of the secant line and then have that approach the slope of the tangent line in order to figure out what the slope of the tangent line should be. Okay, that's kind of the big picture item of what we're doing here. I don't want you to get lost in the details. I want you to still have that visual going on in your head. Okay, so let's capture the idea in the formula. Remember, slope is just rise over run, right? It's y2 minus y1 over x2 minus x1. So what we end up doing is we take y2 minus y1, so f of x minus f of A, over x2 minus x1, x minus A. And what we do is we find the limit of that function as x approaches A. So again, this point, we want that x value to start approaching A. If that x value approaches A to there, right? Actually, this would be a better depiction of that, right? But if the x value approaches the A value, the slope of the secant line is going to approach the slope of the tangent line. Some of you may be thinking in your head, why do I need the slope of the secant line in order to find the slope of the tangent line? Because to get a slope, you need 2 points. In a tangent line, there's only 1 point that you know for sure, right? The whole purpose of a tangent line is it only touches the graph once. So you know nothing about any other point on that line until you know what that line's slope is. So by choosing a secant line, that gives you the ability to get 2 points. And when you have 2 points, you can calculate the slope. Then you can calculate the limit as x approaches A, and that will help you get the secant line slope to turn into the tangent line slope, and thus find the tangent line slope. Okay. Hopefully that helped click a few things in your head visually about what we're doing. Okay. So, a bit strange, but let's repeat what we've already done and in a different way. So that was method 1, okay? Here's method 2. What we're gonna do is we're gonna choose any point on the graph, and we're gonna call that point A, comma, f of A. So far, fairly similar to the last method. Okay? Now, we're gonna label another point anywhere on the graph that is h units away from the x coordinate of A, comma, f of A. Okay? So, any other point anywhere you want. So I just chose to put it there. But what we're saying is from here to here will be h units. So we're going to label that as h. Okay. Now, if that is h units to go from there to there, I want to represent what this point could be. Well, it would have to be a plus h, because I moved over horizontally h units. Okay, so now this point could be represented as a plus h, and then the y value would be plugging that in. So it'd be f of a plus h. Okay. So I have a plus h, comma, f of a plus h. Okay, so now, again, what happens to the slopes of the secant line as we move from a plus h, comma, f of a plus h closer to a, comma, f of h? Well, that secant line, the slope of the secant line will approach the slope of the tangent line. But here's the tricky thing, or not tricky thing, but just this is what makes it method 2. It's slightly different because now we have h involved. What happens to h? Just let me get my pen on again here for a sec. What happens to h as I move it closer to a? H approaches 0 because that distance, as I move that purple point closer to that red point, the distance between the 2 points gets smaller and smaller and smaller until they're right on top of each other, which means h would be then 0. Okay, so for this method, we're still setting up a slope formula, but h will approach 0. So the slope of the secant line approaches the slope of the line tangent to a, and the values for h are getting smaller, so h approaches 0. Okay. All right, so let's do the formula, and it will look like this. So for this guy, it's not a full slope formula anymore, because remember, it's the rise over the run, right? Well, the distance for the run is h. That's why I don't have to go x minus a or a plus h minus a here. Okay, I can just say that's h. And really, if you think about what I just said, a plus h minus a is h. So that's why the h is on the bottom. Okay, so this is still the slope formula. This is still your y2 minus y1 over x2 minus x1. Okay, but the distance h is going to approach 0. Okay. All right. So 2 methods. And remember what we're doing with these methods. We're trying to determine the slope of the tangent. Okay. So in method 1, the slope of a tangent to a curve at x equals a is the limit of the slopes of the secant lines with points that have x values approaching a. Okay, and so we say the slope of the tangent at x equals a is the limit of the slopes of the secants as x approaches a. And to get the slopes of the secant lines, it's f of x minus f of a over x minus a. It's just the slope formula. Okay. In method 2, the slope of a tangent to the curve at the point a comma f of a is the limit of the slopes of the secants with points that have x values a plus h, and h approaches 0. So now we're looking at it from that horizontal distance, and we're getting that horizontal distance smaller and smaller and smaller. Okay, and so the slope of the tangent at a would be given by the limit of f of a plus h minus f of a all over h, where h approaches 0. Okay. So this is exactly what these two fellas did 300 years ago, okay? They didn't have graphing calculators, and so they had to figure out how to get the tangent lines at various points on a graph. And this is what they each figured out, okay? So we're going to take this equation, y equals 2x plus 1, and we're going to go through method 1 and method 2. So we want to figure out the tangent line to the parabola y equals 2x plus 1 at the point 3, 19. Okay, so for the first method, we have the limit of f of x minus f of a, where or all over x minus a, where x is approaching a. Well, what's x? What's f of x? What's a? And what's f of a? Well, x is x. F of x is 2x plus 1. 2x squared plus 1, sorry. A is 3. And f of a is 19. Okay? So I plug all that in. F of x, 2x plus 1, minus f of a, which is f of 3, which is going to be 19. I just wanted to show you where I was getting that. All over x minus a is 3. Okay, so now I'm going to replace f of 3 with my 19. And I'm approaching a, so that's why now the limit is approaching 3. Okay, so this becomes 2x squared minus 18. And now I have to calculate the limit. So I'm right back to what I was doing yesterday. Okay, I can't do direct substitution because that's a non-permissible value. So I want to see if I can factor. I can take a 2 out of the top, and that'd be x squared minus 9, which is factoring into x plus 3x minus 3. That got rid of my problem. The x minus 3 was my problem. So now I can look at the limit as x approaches 3 of 2 times x plus 3. Now I can substitute in, put the 3 in. 3 plus 3 is 6, times 2 is 12. The limit is 12, which means the slope of the tangent line at the point 3, 19 will be 12. So from that point, I could go up 12 over 1 and I'd be back on the tangent line. I could go down 12, back 1, and I'd be back on the tangent line. That is the slope of that tangent line. Okay. All right, now we're going to try method 2. Same question. I should get the same answer. We're just trying it in the different method. Okay. So for method 2, I've got f of a plus h minus f of a all over h, and h is going to approach 0. Okay. So we know that a is 3. We know that f of a is 19. So what I do is I take my f equation. I'm just going to put my ink on here for a sec. So I took my f equation, okay, and I replaced x with a plus h. Well, a is 3, so that's replacing my x with a plus h. 3 plus h squared. You see, f of x would have been 2x squared plus 1, so it's sitting right there. You see what I've done? Okay, so I've written f of x, but I've replaced x with a plus h. Then I know that f of a was 19, so I just plugged that in there. Okay. All right, so now I got to do some cleaning up. And I know that direct substitution isn't going to work right now because I have an h on the bottom. So I have squared that, square the first, double the product, square the last. I'm going to bring the 2 into everything. I also went 1 minus 19. Okay, now I've got 18 minus 18, so that's gone. I'm left with 2h squared plus 12h, which means the h can factor out, which is great because that was the problem. So I just got rid of the problem. Now I can look at the limit as h approaches 0 of 12 plus 2h. So I can now substitute h in for 0 and get 12. So again, the limit is 12, the slope is 12. Okay, the slope of the tangent line at the point 319 is 12. Okay, you got this. All right, so just to show graphically that that is actually what happened. Okay, this is the original equation that I asked you to work with, and I plotted the point 319, and I got computer technology to draw in a tangent line. What I want you to see here is another point on that tangent line is 2, 7. Okay, in order to go from 2, 7 to 319, I went up 12 over 1. Okay, so we can see there that the slope is, in fact, 12. Okay, so this is now how we can calculate the slope of tangent lines using our knowledge of limits that we've done in the last couple of days. So your job is written here. Take your time, make sure you're meticulous with your work, and make sure you're asking lots of questions. Okay, you got this. We'll see you for the next one.